All right, let's look at a little example of something. If I say 10 equals 10, um, wow, that looks like a correct equation, right? Okay, and it is. As long as those two things are unitless, it actually kind of makes sense. Um, Philosophically, though, is there any such thing as unitless? I would say no. Um, some things end up being sort of seeming like unitless, but usually even unitless things tend to be something that can be expressed as something like this, meter per meter, or uh, it's unitless things are usually ratios of things that have units. So if I said 10 cats equals 10 dogs, well, we'd say those two things aren't equal, right? Um, you can't have you can't have equality. This is an untrue statement, not true. Um, it's false. Uh, Mathematics is a language, um, and really equals is the verb of mathematics. Numbers are the adjectives, and units are the nouns. So you got to be very careful with the units. You can't just say 10 equals 10. It's got to be 10 what is equal to 10 what. So let's do an example. Example 1.1 in your text says, show that the expression v equals v sub naught plus at is dimensionally correct, where v and v sub naught represent velocities, a is acceleration, and t is a time interval. How do you do this? I'm going to write down the equation first. V equals v sub naught plus at. And they say v is a velocity. Um, I'm going to actually say, I need an expression for that. Okay, equals is okay if I say v equals velocity of thing. I don't know what the thing is. I'm just going to say that v is the velocity of whatever this thing is that we're describing with this equation. V sub naught is the velocity of the thing when at time t equals 0 seconds. 0 is kind of funny because once you know it's a 0, most of the time you don't even need a unit. If it's 0, um, then it's 0. That's not always true though. Let me show you a counterexample. Here is a circle. Here's a direction. Somebody tells you that direction is theta equals 30 degrees. Well, that's going to be true, 30 degrees, if it is counterclockwise from east. Crap. Okay, let me put that on the screen for you. That angle there is 30 degrees if you measure it counterclockwise from east. Sorry for saying crap. Okay. Um, Somebody else might go, no, that's not 30 degrees. I'm facing this direction, and it's 60 degrees. 60 degrees clockwise from north. So degrees, if I this they'll disagree. They'll disagree because one of them is measuring from one place and another one is measuring from another place. These are relative measurements, and somebody else, and the same thing goes with time. Um, you could say t equals 0 from 0 AD, or you could go, the same time would be t equals 500 years after the reign of Ptolemy the Great. And so time also is not necessarily a relative measure. Um, Time can be a relative measure too. So some things are relative measurements, but other things are going to be absolute. If I have mass equals 0, that's going to be an absolute measurement. Um, if I and Basically anybody that sees that there is nothing there is going to agree that that mass is 0, and it's not going to be dependent on which direction they're facing. It's not going to be dependent on uh, what time they've decided to call 0. If there's nothing there, there's nothing there. Um, Mass length. Length is generally an absolute measurement because you're going to use a ruler, and that ruler is going to measure something. But you might also decide that L is a set of coordinates. And if I said this point was over there, then we could say this point was at x. Say this was 5 meters and this was 3 meters, then you could say x comma y equals 5 comma 3. But somebody else might come along and say that's not true because I'm right here. And he puts his coordinates right there and he says, no, I disagree. X comma y is equal to 0 comma 0. So it's still kind of a relative thing. Okay, so you've got to agree on where your 0 is, the position of the 0. You've got to agree on the position of the 0 on here. So, but I'm getting ahead of myself because I feel like this is something that will be discussed in a later section. But we'll move forward with this example. V equals v sub naught plus at. Here's the thing. Acceleration is a is an acceleration, and t is a time. And what happens when you work out these things, v will be in units of length divided by time, meters per second, feet per second, miles per hour, whatever the length is, a length divided by a time. V sub naught will be the initial speed, which is also in length divided by time. Now, acceleration. There's a few different ways of describing acceleration. Acceleration could be, let's say you go from 0 to 60 miles per hour in 4 seconds. Acceleration equals 0 to 60 miles per hour in 4 seconds. You could write that as 60 miles per hour, and then per second is just right here, second. So that is 60 miles per hour per second. So the units are length divided by time times time. So acceleration, or length over time squared. So I will write length over time squared right there. And then we'll have length over time squared times the time, which is times time. So what happens is time divided by time squared, we'll have uh, sorry, length over time equals length over time plus length over time, because the t over t squared just is 1 over t. So those cancel out, and this does come out to have proper units. Great. Okay, the next question is going to be sort of a little puzzle. Let's pull that up, and it says find a relationship between the acceleration of constant magnitude a, speed v, and distance r from the origin for a particle traveling in a circle. So we've got an acceleration a speed v, and a distance r. A is in, let's just write meters per second squared. We'll go ahead and use the SI units for the moment. That might not be what they do in the textbook, but we'll use that for now. Velocity is in meters per second, and radius is in meters. So how do we put these together in an equation to get everything to cancel out? Well, there's only 1 seconds here. I mean, there's 1 second, there's meters in all of them, but there's seconds in only 2. So we need to find some relationship between these two things, the a and the v, to get the seconds right, and then use the r to correct it. So for this situation, I'm going to say acceleration equals v squared. Now we have second squared on the left, second squared on the right. But this leaves us with meters per second squared on the left and meters squared per second squared on the right. What are we going to do with r to get this correct? Well, if we multiply r over here on this side, then we'll have meters squared per second squared equals meters squared per second squared. So the final answer, we can leave it this form, ra equals v squared. We can decide we want to focus on the acceleration, which would be a equals v squared over r. We could decide we wanted to focus on the radius, r equals v squared over a, or we could decide we want to focus on the velocity, which would be v equals plus or minus square root of ra. So any of those would be solutions to this question. Now this actually does turn out to be the equation for centripetal acceleration. If you have an object going around in a circle, you can actually find that its acceleration is towards the center of that circle, and its acceleration in that direction is equal to its tangential velocity squared divided by the radius of the circle. That doesn't always happen. Sometimes you get an equation where you get the right units, but you don't get there's often a constant between them. Like over here, like for instance, there's a equation for gravity. Force equals m1 m2 over r squared. G m1 m2 over r squared. The force of gravity, this is actually not a good example. But anyway, sometimes after you've got everything worked out, you still need to find out what the units are on some constant. So there's a constant ratio that keeps things together.